All right, we are starting with the first one of the packet, the 2015 third question from the mechanics exam. Here we go. A uniform thin rod of length L and mass M is allowed to pivot about its end, as shown in the figure above. Notice that we have a long thin rod pivoting about one end. We should remember that the moment of inertia should be 1/3 ml squared. A, using integral calculus, derive the rotational inertia for the rod around its end to show that it is ml squared over 3, which is what we expected. So this one we have to remember that the moment of inertia is equal to the sum of the masses times their distance away from the axis of rotation squared. Well, this is a big macro description. It tells us to use integral calculus, so we also have to remember that this is the integral of r squared dm. Moment of inertia is equal to the integral of r squared dm. We did this a little while ago. It's been a while. If you don't remember it, this is a great place to say, holy crap, I have no idea what's going on. Well, it told me the moment of inertia should equal this, so if you just write I equals 1/3 ml squared and move on to B, you'll get no points for A, but you shouldn't lose points in subsequent parts if you know what you're doing in the subsequent parts. So let's finish this out the right way, the integral of r squared dm. Now, if you remember, you cannot take the integral over a axis-less variable. Mass has no axis. This is another one of those things where you have to remember that linear density, because this is basically a line, is equal to mass divided by length. Well, in our case here, we're going to use mu equals r. And since we are taking the derivative, we infinitesimalize everything. dm over dr equals mu. So dm equals mu dr. We're going to have to remember that this is mu in just a little bit. So if we rewrite this dm, it becomes the integral of r squared times mu dr. Well, now we're just taking the integral of r squared. We're going to go from, so we need limits of integration. The rod is L long, so we're going to go from the pivot point is at 0 to the end is at L. I'm going to rewrite the answer here. We have r cubed over 3 from 0 to L times mu. Mu is just a constant, so it doesn't get integrated at all. And if we do r cubed over 3 from L to 0, we should get L cubed over 3 times mu. And remember, mu was m over L. L's cancel. You end up with it equaling ml squared over 3. Now, once again, if you have no idea what I did, if you do not remember that equation, you can just write I equals ml squared over 3. Move on to B. All right, B, the rod is fixed at one end and allowed to fall from a horizontal position A through the vertical position B. Derive an expression for the velocity of the free end of the rod at position B. Express your answer in terms of ml and physical constants as appropriate. Whenever something is dropping from one height to another, think energy. So we're thinking mu g equals k. Question is, what kind of k? Is this rotational, translational, or rolling? It's not translating, so it's not translational or rolling. It is k rotational. mgh equals 1/2 I omega squared. Now, we're looking at this picture. What is the h? When we look at a rod, we have to assume that it is a point mass located at the center of the rod. So it goes from there and it rotates to here. It falls this distance. What is that distance? Well, if the rod is L long, the center of mass is L over 2 away. So we got mg, our h is now L over 2 equals 1/2. It gave us the moment of inertia as ml squared over 3 times omega. It wants the velocity. It didn't say angular velocity, so we're looking for velocity. So we take omega, make it v over r squared. Well, our r is actually L. L squareds go away. 1/2 here goes away here. We end up with MGL equals, make sure I'm getting this right, mv squared over 3. Masses cancel. The 3 goes over. 3GL equals v square rooted. There's your velocity. So I'm going to rewrite it here because it's going to be important. Velocity equals square root of 3GL. All right, an experiment is designed to test the validity of the expression found in part B, that velocity equals equation. A student uses rods of various lengths that all have a uniform mass distribution. The student releases each of the rods from the horizontal position A and uses photo gates to measure the velocity of the free end at position B. The data are recorded below. So we have lengths and we have velocities. Indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate a numerical value for acceleration due to gravity g. We're trying to find g. Well, we've got a couple of things in the way of g. If you keep the equation the way it is, hopefully you recognize that that velocity has to be your horizontal, and we have an L there. That would be that the velocity is the vertical, and L's got to be the horizontal, but it's not just L. It's got to be vertical would be V, and this is square root of L. That's the variable that gives us length and velocity. Me personally, I don't like square roots in equations because they're a little bit confusing, so I can rewrite it as V squared equals 3GL. And if I do that with a different color so it's obvious what I'm doing, V squared equals 3GL. I could have written in the vertical axis V squared and the horizontal axis L. That's what I'm going to do. I don't like square roots. I notice that the coefficient is 3g, so whatever answer I have to divide by 3. Okay, so either answer is correct. Either square root of L and V or L and V squared. Both are the same basic thing. It then says, and I'm sorry, this is on the next page, use the remaining rows in the table above as needed to record any quantities that you indicated that are not given. Label each row you use and include units. So just in case you did square root of L, I'm going to give that to you. And that would be square root of meters, I guess. And then I used V squared, and that would be meters per second squared. Okay, so root of L, if you do the square root of the L, it gives you 0.5, 0.707, 0.866, that's just 1, 1.118, and 1.225. V squareds, 7.29, 14.44, 21.16, 27.04, 33.64, and 39.69. Okay, now part C says plot the straight line data points on the grid below. Clearly scale and label all axes, including units as appropriate. Draw a straight line that best represents the data. Okay, so for my graph, like I said, I used L, which is measured in meters, and then I used velocity, measured in meters per second squared. Sorry, that's velocity squared. I want to use as much of the graph as possible. For L, it goes from 0 to 1.5, and it gives us 1, 2, 3, 4, 5, 6 separate things, so we can use 0, 0.25, 0.5, 0.75, 1, 1.25, 1.5. The great thing about this data is each and every data point is going to be straight on a line. I don't have to find spaces in between. Now my velocity goes from basically 0 all the way up to 40. And I've been given, I don't know what this is, sorry about that. 1, 2, 3, 4, 5 separate parts, 40 divided by 5. I guess that's 8, but I went ahead and just went 10, 20, 30, 40, and 50. You can probably go by 8 and get all the way to 40, but who cares? Let's keep going. Now we plot our data. I'm using data I wrote down on a piece of paper. You might have to flip back and forth, my bad. you would have a point here. Didn't draw. There we go. You would have a point here-ish. You would have a point here-ish. A point here-ish. Point here, and then all the way up here, like so. Now, be very careful. Draw as straight a line as you can. On this tablet, it's going to be tough. So I'm going to do my best. And you know what? I'm just not even going to try too hard. That's what I got. It's not great. It's not exact. It's not precise, but hopefully you'll understand. Now, when I did this on my piece of paper, it actually came right through that point there. And the next best point I found was that point there. Let me keep going. I use your straight line to determine the experimental value of G. Remember, when you're finding stuff like this, do not use the data points. They don't care about the data points. They care about your line. My line went through 0, 2. I know it doesn't look like it does here, but just hit the believe button. And then it's 1.45 up here and 38. I chose these because they are very clear, very obvious. Now, straight line. Our equation is v squared equals 3GL. This is our slope m, and that's equal to y2 minus y1 over x2 minus x1, which happens to be 0. I end up with 24.8276. Please remember it's 3GL, so you have to divide by 3, and I end up with a G equal to 8.28 meters per second squared. All right, sorry for the pause. I got a text, as you heard. Okay. I describe 2 ways in which the effects of air resistance could be reduced. And I had what they wrote down. I think I did not bring that with me. Okay, some of the ways that they wrote down. You could use smaller length rods. You could use a more aerodynamic object. You could do it, perform in a vacuum, and that is, I believe, the things that I remember from that. All right, that's the first one. Hopefully you got through this pretty okay. Start the next video when you are ready.